Okay, good afternoon, everyone. I'm sincerely hoping that people can hear me and that you can see me as well, and that we are live. This is the last of our 6 paper 1 sessions, and it's all about functions. And I always spell functions capital F, capital U, capital N, because I really think they are quite a lot of fun. So, welcome to all of you. Yeah, the reason I'm sort of laughing to myself is someone's just pointed out to me that yesterday when I was doing counting techniques, I counted the letters in mathematical and came up with 11 as an answer. And yeah, if you're gonna do well in counting techniques, then you do need to be able to count. Right, there are actually 12 letters in the word mathematical. Anyway, we're not talking about counting techniques today. We're diving straight in to our functions. But just before we do, just a reminder of how this all works in case you happen to be watching this one first. All the questions that we're going to answer each day are available for download at simi.education. Right, and ideal best practice is for you to actually try the questions yourself before you watch the video. Right, and obviously you can watch the video either in the live stream or you could watch a recording thereof. If you do watch a recording, try and watch it kind of actively. In other words, pause, try things, and then let it run. Don't just sort of keep it playing in the background because it is quite easy to disengage. Okay, so let's dive in. And what we've done uh, each day is we've looked at the kind of the formulae that we get given, and I've sort of scoured the formula sheet. These are not all together in the same place on the formula sheet, and in fact, three of them come from the analytical geometry sort of section of the formula sheet. But these are really the only three formulae that we get provided: the quadratic formula for solving a quadratic equation, obviously, a formula for gradient, and then two different options for a formula for a straight line. Okay, so we going to now just look at some of the sort of uh, the fundamentals of functions, right? And the first thing is exactly what is a function? Well, a function is a rule such that each input uniquely defines a single output, right? And we for a function, it is a case that we can draw a vertical line over the graph without it touching it more than one point at a time. Okay, now you get different types of functions, okay? The first one, the red one there, is a non-function, right? Because we cannot pass a vertical line over the graph without it cutting the graph at more than one point, right? The green one is a function, as is the blue one, but they're interestingly different. The green one is what is called a one-to-one function. Every input produces only one output, right? That's really a really important idea. Notice the green one, in addition to passing a vertical line test, also passes a horizontal line test, right? When you've already tested that it is a function, and it then passes a horizontal line test too, it's a one-to-one function. Now, the important thing with one-to-one is that when you find an inverse, it's one-to-one, and you'll have a function. That blue one at the end is many-to-one. It's a parabola, all right? There are many inputs that get the same output. That's not a problem. It's still a function. But if you have many to one, all right, that's fine. And I'm hoping this is showing kind of left to right on your screen. Okay, many to one, all right? But when you find the inverse of that, you end up with a one too many, all right? And it's a non-function. And the only way you can kind of sort of prevent that happening, sorry, trying to work out where my hands are. The only way you can prevent that happening is to restrict the domain of the blue thing, of that blue function, to make it one to one, all right? And so you could either take only the left-hand half of the parabola, all right? In other words, x less than or equal to 0, or the right-hand half, x greater than or equal to 0. But we'll get into that shortly. All right, the next really important idea is domain and range. Domain are the things that you can put into your machine, or your function machine, in the same way that you can't kind of put a smoothie or fruit into a toaster, all right? You can't put certain things into certain function machines. And then the range is the things that you can kind of get out of the possible outputs. Okay, and we typically write domain is always about x, so x element of R, and then followed by any restrictions. So that's been repeated there. and range y is an element of R followed by any restrictions. Okay, right. The next thing, which is really, really important, okay, is, sorry, that's been repeated there. Sorry. If we want to draw a function, we can always find a y-intercept by letting x be naught. We can find our x-intercepts. There might be more than one by letting y equal naught, right? Y-intercept by letting x equal naught. X-intercepts by letting y equal naught. And then x coordinates of our stationary points by letting our gradient be naught. dy by dx equals naught, right? So although we're doing functions, we might well end up doing a little bit of calculus as well. The next thing is transformations, and to transform means to change something. And these are kind of best described with some examples. So we've got a function here, x squared plus 2x plus 6. If we put a negative in front of every x, in other words, we work out f of minus x, a negative in front of the x reflects the graph in the y-axis. All right. If we put a negative in front of the whole thing, in front of y, it reflects the graph in the x-axis. If we work out f of x plus p, in other words, we add p to every x value, and I want you to notice that all the x values, x plus p, all squared plus 2x plus p, right, that will shift the function left or right. And this left-right shift is a little bit kind of counterintuitive in that if you add, it actually shifts it left, okay? And if you subtract, it shifts it right. I'm worried about whether which way my finger's moving on the recording, but I hope it's not being inverted. But okay, all right. And then if we add a number at the back, in other words, f of x plus q, that shifts the function up and down. And that one's more kind of intuitive in the sense that if we add, it goes up, and if we subtract, it goes down. Okay, right. That's all generally true for all functions. Next up, we're going to look at the specific some specific functions. All right, and I'm calling them our friendly functions, right? And they really need to be recognizable to us like old friends. Okay, I'm going to show you some sort of dynamic simulations of each of them. But the first one, the straight line, the linear function. Essentially 5 of these. All right, y equals mx plus c is what we call the standard form. M is the gradient, as we know, gradient that's going a positive gradient rather, the green graph, green lines sloping uphill, and a negative gradient, the black line, sloping downhill. Typical domain is that x can be anything, and typical range is that y can be anything. All right, it goes as far left and right domain as we like, and it goes as far up and down range as we like. Okay, typically. All right. The next one that we're going to look at is our quadratic function, the parabola, ax squared plus bx plus c. Remember, the sign of a determines whether the graph is concave up, like a cup, or concave down, like a frown. I'm really struggling to find out where my hands are. Okay, all right. And the parent function, what I actually often refer to as the vanilla flavored function without any sort of adjustments, is ax squared. The standard form is ax squared plus bx plus c. And the typical domain, left and right, can go as far left and right as we like. But the typical range depends on the turning point and the concavity, all right? Because obviously, if it's a concave up one, it won't go below the turning point. If it's a concave down one, it won't go above the turning point. Okay, makes sense? It always makes sense. Isibalo, zikfanteke injalo. Okay, and then the last thing is just this idea of an axis of symmetry. It's got an axis of symmetry. It's not like a kind of Nike swoosh thing. It's symmetrical, all right? And that axis of symmetry has an equation of negative b over 2a. All right, next up, the hyperbolic function, or hyperbola. This looks really kind of messy, but there's essentially 2 that have been plotted here. There's a green one, which is in quadrants 1 and 3, if we use the trig numbering for quadrants. All right, and then there's the black one, which is in quadrants 2 and 4. Okay, and both of them have a domain of anything other than 0 and a range of anything other than 0. Okay, both have y equals x, a line with a gradient of 1, and y equals minus x, a line with a gradient of minus 1, as axes of symmetry. Right. And those points that I've referred to as salient points are actually the points where it's closest to the origin, if it hasn't been moved, right? And they are basically the square root of our K value. Okay, but we'll sort of look at this as we kind of draw one or two. Okay, right. Next up, the exponential function, and you might remember when we did exponents, I was saying it's all about that base, about that base, about that base. The base, if the base is bigger than 1, our graph will go uphill as we look at it, left to right, right? And if our base is less than 1, our graph will go downhill as we look at it, left to right. The base cannot equal 1, and the base may not be negative. Typical domain, x can be anything. We can go as far left and right as we like. Typical range, all right, above a certain value or below a certain value. Okay, and we'll dig a bit into that as well. And then the last one is the log graph, right? And the difference, you might say, well, Paul, what's the difference between a log graph and an exponential graph? Exponential graphs have got horizontal asymptotes, and I should have mentioned that now. Log graphs have got vertical asymptotes. So it's really dead easy to pick which is which. But remember that the base is going to tell us again, if the base is bigger than 1, even if we have a log graph, the log graph will go uphill, left to right. If the base is less than 1, the log graph will go downhill, left to right. Okay, now what I'm going to do is I'm going to talk us through and just show you some simulations of each of these graphs. So here's the first one. This is our straight line graph. The gradient we can change. You can see the equation. Okay, you're not seeing the equation, which is a shame on this particular one. All right, and you can see there we go, there's the equation coming in now. All right, there's the equation, and you can see mx plus c, gradient, and y-intercept. Okay, right, the next one that we're going to look at is the quadratic function, and I'm actually going to show you two sort of versions of this sketch. All right, the vanilla is just x squared. All right, if we make a bigger, you'll see that the graph just gets kind of tighter, the gradient gets steeper. If we make a negative, as you know, the graph goes concave down. Okay, I'm going to leave it at concave up, all right? And I'm also going to ask, now I'm going to add a number at the back, and I want you to notice how I'm going to add a number at the back. I'm going to add a number at the back, and you'll notice how the equation is being altered as I shift the graph. It just shifts the graph up or down. Okay, I'm going to now add a number to the x's before applying the function. So in other words, inside the bracket there. So if I go x plus 3, right, what you'll notice is that the graph's actually shifted across 3 to the left, right? And this is what we refer to as the sort of turning point form, right? And you'll notice that the turning point is -3, -2, because this graph, which used to be it used to turn on the origin, the parent function, the vanilla one, now it's been shifted 3 to the left and 2 down. And if you move that point off the origin 3 to the left and 2 down, you get to -3, -2. Notice the range. The range is y bigger than or equal to that y value of the turning point. If the graph was a kind of a sad graph, a concave down graph, as it's actually better called, all right. And I'm just going to pull it up here, and I'm hoping we'll see we're actually not seeing the equation, but what we are seeing is the range. The domain, x can be anything. We can show the intercepts with the axes, all right? We can show the axis of symmetry, and the axis of symmetry is just x equal to the x coordinate of the turning point. What we can also show, all right, is we can show the discriminant, delta. Remember our nature of roots. Now, at the moment, delta is 7. And remember, if delta is 7, then we are going to get 2 x-intercepts unequal and, in fact, irrational. I want you to watch what happens if I drop this graph down slightly. Right, if I drop it down just the requisite amount, I might get delta equals 0. Because remember, when delta equals 0, I get equal roots. If I drop it down a little bit more, you'll see delta goes negative. Okay, the next one I want to show you is also the quadratic function. All right, but this one is not in this was just in A, B, and C form. All right, and notice straight up, delta, all right, is negative. It's not touching the axis. If I sort of bring it down a bit, you'll notice that now delta is positive. Okay, people often ask me, Paul, what does B actually do? And I'm going to show you what B does. All right, we know what A does. A turns the graph kind of happy or sad, concave up or concave down, and also affects the sort of steepness. B affects the axis of symmetry in tandem with A. All right, and notice that delta is positive for all these values. If you change B fascinatingly, the parabola actually moves on a parabola, which is kind of quite cool, all right? But notice that if B is 0, then your axis of symmetry is 0. Because remember, the axis of symmetry is negative B over 2A. At the moment, we're not really seeing the axis of symmetry. There it is there. Okay, but if B is 0, then the graph is it's symmetrical about the y-axis. Okay, so down the bottom corner here are the domain and range, right? And you can see the range is bigger than or equal to the y value of the turning point, right? The c value gives us the y-intercept. No rocket science there. To find a y-intercept of any function, you're going to let x equals 0, and obviously y would just equal -5. All right, the next one we're going to look at is the hyperbola. Here it is. Okay. And yeah, so this one has not been shifted horizontally or vertically. The asymptotes are the axes, and notice that k is the value on the top here. The point that I'm plotting, those 2 points there, I'm going to make k equal to 9. All right, and you'll see that those 2 points are 3 and 3. Sorry, 3, 3, and -3, -3. They are the points where this thing is, this thing's been slightly sort of stretched. Unfortunately, the 2 on the x is not quite the same size as the 2 on the y. All right, I'm not going to try and fix that now because it might just go pear-shaped, right? More pear-shaped. Okay, but what I can show, there are no intercepts of the axes at the moment, all right? But I can now, if I wanted to show you that if I make k -9, all right, this thing hops. I'm in fact going to make k -7, -16. Now, if you square root 16, not -16, if you square root 16, then you get 4. And in this case, these salient points are -4 and 4, and 4 and -4. All right, I'm going to show the axes of symmetry for this graph. There they are, and this is what I'm worried about a little bit with yeah, they're meant to be at 45 degrees. Okay, and I apologize, they're not. All right. Notice that if I change the value of k, the axes of symmetry are the same for all hyperbolas until they move. All right. Now, I'm going to make this back to a nice sort of reasonable number like 9, so we can just sort of see what's happening. All right, that 9. Okay, and now I want you to see what happens if we shift the graph upwards. Right? Notice, and I'm also going to in fact shift it something to the kind of 2 to the left. Okay, in fact I'm going to shift it 3 to the left. When you look at the equation, there's the equation: 9 over x minus 3. Sorry, 3 to the right. Okay, and plus 2, shifting it 2 up. Notice that our axes of symmetry always go through the intersection of the asymptotes. So in other words, they're going to go through that point of 3, 2. One's got a gradient of 1, one's got a gradient of -1. Okay, right, we'll come back to that. The next one, the exponential graph, and we spoke about it. We said basically it's all about the base. Notice that if the base is bigger than 1, the graph goes uphill. If the base is less than 1, the graph goes downhill. Notice at the moment that the domain is x can be anything. It goes as far left and right as we like. Range, y bigger than 0. But if I start shifting the graph up, notice the range is bigger than the asymptote. So that number at the back tells us the asymptote. All right. And now the range is bigger than that. Okay. All right. I'm going to show you another exponential graph because this one's just b to the x. The sort of standard form's actually ab to the x. And the really interesting thing is like, well, what does the a actually count for? All right. And I'm going to show you what the a counts for. All right. Okay, so obviously this is our base. We can make the base sort of bigger or smaller. Notice that's not affecting the y-intercept. All right, but if I change the value of a, it actually moves the graph to the left or to the right. Okay, which is not immediately obvious, and I'm going to explain to you why that would be the case. When I've got kind of the pen in front of me just now, I'll show you that. There's an asymptote, all right, and obviously the intercepts of the axes. And if I drop the graph, you can see the asymptote, and you can see the intercepts of the axes. Last one that I want to look at is our log graph, all right? And the log graph is the inverse of the exponential graph. So I'm gonna go with a vanilla flavored uh, exponential graph with an a value of 1. I'm going to go with a b value of 2, say. All right. And I'm going to go with a c value of 0. So this is very much just like 2 to the x. There it is. 1 times 2 to the x. Okay, I'm going to show you the inverse function. That is the log base 2x function. Notice both of them got a base of 2, so they're both going uphill. The big difference is that the exponential function has got a horizontal asymptote. The log function has got a vertical asymptote. I want to show you, now just listen carefully to what I'm going to say now. They are inverse functions of one another, all right? Exponential and log. The domain, listen carefully, the domain of the exponential function is that x can be anything, and the range is that y has to be bigger than 0. When you find the inverse, those things swap around. What were outputs become inputs, and what were inputs become outputs. So notice that the domain of the log graph is x bigger than 0, and that's because the range of the exponential graph was y bigger than 0. I want to show you what happens if I move the exponential graph up by 2. Let's go up by 2. Yeah. All right. Notice, so I'm on 2.1. Notice the equation. Okay, it's picked up by 2. All right. But notice that the log graph's gone right by 2, and that makes perfect sense. It always will. Okay, because the domain of, listen carefully to this, the domain of the exponential function is still y can be anything. So the range of the blue log function is, sorry, the domain of the green exponential function is x can be anything. So the range of the blue log function is y can be anything. The range of the green exponential function is y bigger than 2, and therefore the domain of the blue log function is x bigger than 2. Okay, the last thing I want to just talk about is reflections. All right, and I'm going to show you this, which is cool. Remember the idea of reflections. Here's the equation of this particular thing. I want to show you that if I show the reflection in the x-axis, I want to show you where, disconnect, sorry, and delete this, sorry. Delete that text. It's actually irritating me and getting in my way. All right. Notice where the negative is, and that's a reflection in the x-axis. I can drag the green one, but the red one's always going to be a reflection, and you can see that it's a reflection, okay? All right, notice where the negative is. I'm trying to show you unfortunately, the equation on the green one's just falling off the bottom of the screen here. But you can see the negatives right in front of all of it, okay? Now, I'm going to turn that one off, and I'm going to show a reflection on the y-axis. And the reflection on the y-axis is going to be exactly the same equation as is right at the bottom of the screen here. And I'm sorry it's not letting me drag it up, but it's going to have a negative in front of every x. Look at it. There it is. It's the same equation, but it's got a negative in front of every x. It's a reflection on the y-axis. If I drag the blue one drags across as well. Okay, so that's how that works. And the last type of reflection is an inverse, is a reflection in the line y equals x. So notice every point, I'm just going to take a point and let's see if I can, I'm going to drag this, sorry, I'm going to drag this green one. Okay, I'm going to drag this green one so that it's going through this point over here. 2, 1. Notice there, sorry, not 2, 1, 3, 1. Swap 3, 1 around and you get 1, 3. And so notice that they are at 90. There are reflections over the line y equals x. Once again, this dotted line should actually be at 45 degrees. Okay, right. Now, finally, we're ready to answer some questions. I'm hoping that was kind of useful background. And so I'm going to put up my, always try and do this kind of seamlessly, and I don't get it right ever. Okay, Alt 9 for that. Okay, there we are. Right. My memo, my solutions, my cheat sheet has fallen off onto the floor here. So I'm just going to quickly grab that. Right. Okay. I was actually hoping to have a slightly different scene where you would have seen my face. You're not seeing my face, but maybe that's already for your. Okay, let's have a look at these functions. The first thing is just understanding kind of function notation and how it works. Remember what f of 3 means is put 3 in for all values of x in f. Right, so this is going to be 2 lots of 3 plus 6 minus g of 4. G of 4 means put 4 in for all the x's there. Right, we get 2 lots of 9, which is 18, minus 16, we actually get 2. The next thing that's important and interesting is that a function can actually take the output of a previous function. So in other words, f of 2 means put 2 into x, right? And when you put 2 into x, you get 2 into f, rather, you get 2 plus 6. So now we're actually working out g of 8, right? And g of 8 means 8 squared, and we get 64. This is basic understanding of how the function notation works, but really important. The next one says, what must m be if f of m is equal to g of m? Right, or g of m is equal to f of m. G of m is actually m squared. F of m is m plus 6. All right, all I've done is I've replaced the x's with m's, and now I'm just solving this little quadratic equation. Okay, and because I've spent quite a lot of time up front on all the function stuff, so what I'm going to do here is I'm actually just going to shortcut some things here. This is going to be m equals 3 or negative 2. Right, the next one is what's the range of h? Now, h is this thing over here. And this is where these functions need to be like old friends to us. I'm going to think of what 2 to the x plus 3 looks like if I had to draw it. First thing, it's not a parabola. It's not a hyperbola. It is, in fact, an exponential graph. Which way is it sloping? It's sloping uphill. All right. What does the plus 3 do? It picks it up by 3. Right. So do you see why you need to know exactly what each of these functions look like? Here's a very rough sketch graph of 2 to the x plus 3. This line over here being y equals 3. What's the range? Well, the range is y can be an element of the real numbers, but in fact, y must be bigger than 3. Not bigger than or equal to 3. It doesn't actually touch the asymptote. The domain of J, let's just look at what J is. J is a log graph. Now, you cannot find the log of a negative number, and you cannot even, in fact, find the log of 0. So in here, we need to have a number that's bigger than 0. In other words, x minus 2 must be bigger than 0. All right? And therefore, x must be bigger than 2. So our domain is actually x can be an element of the real numbers. What we're saying there is we're saying it doesn't have to only be whole numbers. It can be any type of number. In other words, irrational or rational, all right? But it must be bigger than 2. Then it says, which of these functions has an axis or axes of symmetry? Right. And the 2 that have axes of symmetry are g, right, a parabola, and k, a hyperbola. Right. The hyperbola has actually got 2, right? But the answer to that, g and k. Right, then it says, which of these functions does not have an inverse, which is a function? Right, that's really poorly worded. What it should probably say is, which of these functions has an inverse, which is not a function? Okay, so it's not great English at all. All right, and remember, the parabola is actually in paper 1 the only many-to-one function that we study. No, it's not. The cubic function is also okay, but of these ones, of these 5 that I've spoken about, the parabola is the one that's kind of fails a horizontal line test. Okay, so the answer to that last question there is G. Right. Next up, we are going to look at these functions here, and we are going to try and write them into their turning point form. I'm going to do them both sort of at the same time, all right, which I hope I don't confuse people by doing that, but I'm going to try and write them like this. Okay, and we completed the square on a previous occasion to solve an equation. We completed the square when we did the analytical geometry to put a circle into standard form. And here we're going to complete the square one more time to put a parabola into turning point form. Right. I know that whatever I put here when I square up is going to double, so I must put 3. If I square this out right now, I'm going to get a 9 that I didn't have before, and I'm going to subtract 9. Now, you might say, Paul, didn't you add 9 last time? Yeah, last time we were talking about an equation, and we'd added it to the left, so we needed to add it to the right. This is actually x plus 3 all squared plus 2. Okay, I'm going to do the other one next door. I'm going to do it in blue pen, and that one is slightly problematic because it's got this -2. So what I'm going to do is I'm going to factor out the -2. All right, I can't divide it out. If I divide it out, then I haven't got y anymore, and I want an expression for y. This is going to be x squared minus 5 over 2x minus 3 over 2. If you multiply that -2 back in, you get this thing. Okay, you're not changing the value at all. Now I'm ready to complete the square, but I'm going to operate now inside the square brackets. And remember what I want to do? I want to halve the coefficient of x. So it's actually going to be x minus, the best way of, don't go to decimals here, don't go to 2.5, all right? And it's the best way of halving a fraction, if the top is not even, is to double the bottom. All right, just remind you that half of meaning times 5 over 2, 5 over 4. The bottom ends up doubling. Okay, now, if I square this out, I've actually inadvertently added in 25 over 16, which is 5 over 4 squared. So I now need to subtract that, okay, in order to make this thing multiply back to what it was. And I've still got the -3 over 2 here. Okay, so there it is. That's how it looks. Now I'm going to add these two fractions. I'm going to, 3 over 2 is the same as 24 over 16. And when I subtract 24 from 25, I actually get minus 49 over 16. But many of you will do that on your calculator, and it's not a train smash. It would be nice if you could do it without. All right, x squared minus 5 over 4 all squared. And now I'm going to multiply the -2 back in. Okay, minus 2x squared minus, sorry guys, this is not x squared. That is absolute drivel. Drivel of the highest order. Sorry, that is not x squared. Okay, I'm getting a bit over enthusiastic with my squares. Right, there it is, x minus 5 over 4 squared. Now, when you multiply -2 by minus 49 over 16, you actually get plus 49 over 8. Now I want to talk about these two graphs. This red one is actually just y equals x squared. Now where does y equals x squared turn? It turns at 0, 0. Okay, but it's been shifted. It's not y equals, this is y equals x squared. We're not dealing with y equals x squared. We're dealing with the same shaped graph, exactly the same tightness, all right? But it's been shifted. This one here, has actually been shifted. How? 3 left and 2 up. And if it's been shifted 3 left and 2 up, then that turning point that was at 0, 0 will become -3, 2. Okay, I'm going to go through exactly the same discussion here. Here we've got the graph -2x squared. -2x squared is just a tighter version. It's kind of steeper than the -x squared. It turns at 0, 0. So what I've drawn over here is y equals -2x squared. That's kind of like the parent function. Okay, but that's not what we're dealing with. We're dealing with the same shape graph, the same kind of, I got shouted at once for calling a parabola a shape. All parabolas are the same shape, wasn't it? I can't remember what the problem was, but okay. Basically, our graph now has been moved 5 over 4 to the right and 49 over 8 up. And so our turning point that used to be at 5 over 4, at 0, 0, is now going to be, our turning point is going to be 5 over 4, 49 over 8. Okay, right. Onwards and upwards to question 3. And question 3 looks like this, right? And it says, a function is shifted 3 units right and 2 units up, and then the result is reflected in the x-axis. What's the final sort of equation? Well, if we think about it, I'm going to call the new function g of x, okay? G of x is actually going to be f of x plus, sorry, not plus, we want to shift it right, f of x minus 3, right? And then I must add 2. That's going to move it up 2, right? And then, after I've done all of that, I want to reflect it in the x-axis. So I'm going to put a negative. You could think of putting the negative here, which is in front of the y, or there, same thing. Okay, that will reflect it. Okay, now our functions actually, remember f of x is x squared plus 5x minus 2. F of x minus 3 put x minus 3 in place of all the x's. X minus 3 all squared plus 5 lots of x minus 3 minus 2. All right, and then plus 2. Okay, the plus 2 is the plus 2 that's picking it up. Now, the last thing I've got to do is just put this thing into standard form. And it strikes me that squaring a binomial, and I've spoken about this in just about every video, is something we really want to be able to do fluently. X squared, that product doubled, 6x, negative 6x, plus 9, plus 5x minus 15. And then we've got a minus 2 and a plus 2. Right. We actually end up with negative of x squared minus 6x plus 5x is minus x, right? We've got 9 minus 15, which is minus 6. And then we're going to reflect it over the x-axis by multiplying this minus, and then we get negative x squared plus x plus 6. Okay, and that's question number 3. Onwards and upwards to question number 4. Right, question number 4 looks like this. It says, find the equation of the axes of symmetry of this. Okay, now there are 2 ways of thinking about this, all right? But I think the easiest way, and so I'm only going to, you'll see if you look at the memo, you'll see both ways, all right? I think the easiest way is actually to realize that if we had to draw this graph, the axes of symmetry, sorry, the asymptotes are negative 3 and negative 8. Somewhere there and like somewhere down here. Okay, this line is y equals negative 8. This line is x equals negative 3. This, by the way, is a hyperbola in quadrants 2 and 4, right? But it's been shifted 3 to the left and 8 down. So it's gonna look something like this. Don't do what I've just done there and suggest that this is bending away from the asymptote. It doesn't do that. All right, it does that. Okay, and over here it does something like this. Now, our axes of symmetry, and you don't need to draw this whole picture, right? Our axes of symmetry have gradients of, so I just wanted to draw that a different color, have gradients of -1 and 1. But they both go through this point, and this point is going to be the point -3, -8. So I literally want lines with gradients of 1 and -1, and they must both pass through this point -3, -8. All right, and so I like to, as you know from, I think from our analytical geometry, I actually like this y minus a y value. So y minus minus 8 is equal to the gradient. I'm doing the positive one first. X minus an x value, x plus 3. That's the one. And the other one, just change it to a green pen, is going to be y minus minus 8 is equal to the -1, all right? X minus minus 3, x plus 3. And so what we get, when we simplify them, this one, let's do this one first, thing is I've got the green pen in my hand, negative x, this is -3 minus another 8 minus 11, all right? And this one, y equals x, and we've got an 8 on this side that we're going to subtract, and we end up getting y equals x minus 5. Okay. Axes of symmetry, really, really important. Right. Next up is finding the equations of inverses, right? And there's a little sort of idea here that what you do, the first thing you do is you write it as y equals, right? And before I even start one of these, what I like to do just for fun, because one can, I find a point. I just work out a point on this function. So on this particular function, if x was 5, minus 2 dots of 5, negative 10 plus 3, I get negative 7. I'm going to check when I'm done that if I put negative 7 into my inverse, I get 5 out, because that's exactly what an inverse does. It returns the original thing. Okay, so because I want these two numbers to swap around, I swap x and y around. It makes sense. It always makes sense. X is minus 2y plus 3. And now I solve for y. I make y the subject of the formula. I'm just solving an equation. I'm just getting y on its own. I'm going to subtract 3 from both sides. All right? And lastly, I'm going to divide both sides by negative 2. So what I actually get is y equals x minus 3 over negative 2. Right, it is an algebraic kind of trick that you can sort of swap that around and change the sign in front of it. So in other words, you could actually make this 3 minus x over 2. They're the same. Those are algebraically equivalent. Now, that is our inverse. Just be careful. The question actually asked for us to write it as f inverse of x equals. So I'm going to go with 3 minus x over 2. It doesn't matter which one I go with. Right, and I want to show you that if you put negative 7 in here, 3 minus 7 is 3 plus 7, it's 10 over 2, it's 5. Bingo. Okay, the next one we're going to look at is a log graph, right? Exactly the same idea. I'm going to, just because I can, I'm going to start off and I'm going to, if x was 4, all right? 4 minus 3, yeah, I'm not going to actually go with 4. So I'm going to go with just 4. I'm going to go with 7, actually. And the reason I'm going with 7 is that if I go with 7, I get 4 in the bracket. Log base 2 of 4 means what power must I put onto 2 to get 4? And the answer is 2, right? So this all comes to 2. And lo and behold, I actually get 7 out. Okay, right, so 7, 7. Now, possibly not the best point of use, but I'm going to check that if I put 7, this output, into my final answer, that I get this input out. Okay, all right, let's have a look. So I'm going to change this to y equals exactly like I did last time, log base 2 of x minus 3 plus 5. I'm going to swap x and y around exactly like I did last time, log base 2 of y minus 3 plus 5. Now I need to get the y on its own. I'm going to take it out of log form and put it into exponent form. The base is always the base. I'm just checking this out. I'm going to subtract 5 from both sides first. X minus 5 equals log base 2 of y minus 3. Okay, and get, now I'm going to take it into exponent form. The base is always the base. So 2 to the x minus 5 is y minus 3. All right, and therefore y equals 2 to the x minus 5 plus 3. And lastly, remember they asked us to write it as f inverse of x is 2 to the x minus 5, x minus 5 plus 3. Okay, what I'm going to do is I'm going to put that 7, all right, I know they're both 7. I'm going to put that 7 into this thing. 7 minus 5 is 2, 2 squared is 4, 4 plus 3 is 7, and lo and behold, when I do that, I get this 7 out. Okay, I know they're both 7s. Okay, I'm just satisfying myself that they actually, one's gone in and one's gone out. Okay, there we go. Now, x squared plus 4, right? That, if we just picture it, it fails a horizontal line test. It's a many to one function. What I'm going to do, I'm going to only take a half of this thing. Okay, I'm only going to take that. All right, and that means that I'm going to make the domain of this original thing x bigger than or equal to 0. Now, when I do that, remember that the domain of your function is going to become the range of your inverse. So I know that the range of my inverse is actually going to be y bigger than or equal to 0. Y bigger than or equal to 0. Okay, but apart from that, we proceed exactly as normal. I'm going to write it as y equals x squared plus 4. I'm going to swap x and y around just like last time. I'm going to solve for y, so x minus 4 is y squared. And I'm going to square root both sides. Now, when you square root both sides, you can normally have plus or minus, okay? But I'm not going to have the plus or minus because my range is y bigger than or equal to x minus 4, all right? And there's my answer. The last thing I must just make sure is that I do write it in the form that they asked for it. Positive root x minus 4. Just to show you kind of graphically what we've got here, our inverse is up there. It's only the positive half. If we had only gone for the left-hand side of the parabola, in other words, we had restricted our domain the other way, we would have crossed out the right-hand side and we would only have had the left-hand side. Our domain would have been strictly negative, which means our range would have been strictly negative, and we would have got the other half. We would have got a minus in there, and we would have got the bottom half of the parabola. You can choose, but you've obviously got to make sure that you get the correct corresponding inverse. Okay. All right. In the memo that will go up straight after the session, I've actually done both. Okay. So there it is. Just because we can, I'm going to go and check. If you put, say, for example, 3 into here, into the original function, you get 3 squared. 9 plus 4, you get 13. If you go and put 13 into this thing, 13 minus 4 is 9, square rooted is 3. La. Okay. F of x equals 2 to the x plus 3. Right. Again, just because I can, I'm going to make up an x value. 2 cubed is 8, plus 3 is 11. I want to make sure that when I get an answer, 11, when I put 11 into my answer, I get 3 out. Okay. Remember, change f of x to y. Y is 2 to the x plus 3. Swap x and y around. X is 2 to the y plus 3. Solve for y. So x minus 3 is 2 to the y. Now I'm going to go into log form. The base is always the base. So log base 2, x minus 3 is equal to y. Okay. And therefore, to write it in the kind of correct form as I asked for, the inverse function of f is actually log base 2 of x minus 3. All right. And when I put 11 in here, I get log base 2 of 8. And remember what log base 2 of 8 means. It means what power must I put onto 2 to get 8? And the answer is 3. And that is exactly what I was hoping for. Okay, right, question number 6. Right, cool question. It asks us, they've drawn us some functions and they ask for this sort of transformation function, okay, that results. So over here, f of x plus 7 minus 4, this is f of x, right? Adding 7 to the x values and subtracting 4, this thing is going to move 7 to the left and 4 down. The point that I'm really going to focus on is this one over here. It's at 3, so it's going to go to minus 4 if I move it 7 left. It's at 2, and if I move it 4 down, it's going to go to there. So my graph's going to turn somewhere there. It's actually going to be exactly the same shape. It's just shifted and shifted. Next one, y equals the negative of f of x. I want to just reinforce something with you here. Do you agree that algebraically that's exactly the same as that? We've actually got a negative in front of the y. When we put a negative in front of the y, our graph reflects over the x-axis. Right, so it's going to do something like that. Okay, you don't have to get it 100% correct. I think that conveys, that graph that I've drawn conveys an understanding that it's reflected over the x-axis. This one, f inverse of x. This one needs to reflect about the line y equals x. And because of that, I'm actually going to try and draw in just to guide myself a little bit here. That. Okay. All right. This thing had a y-intercept of 1. The inverse, I'll just draw the inverse in red. The inverse will have an x-intercept of 1. This thing had a horizontal asymptote of y equals 0. The inverse will have a vertical asymptote of x equals 0. This is actually a log graph that I'm drawing here, and the other one was an exponential graph. I want to draw your attention to that point. It was 2, 4. Swap 2, 4 around, you get 4, 2. It's going to go somewhere like that. And what you should be seeing is a reflection around this blue line, y equals x. All right. a function and its inverse are always reflections of one another around that line y equals x. Okay, this is another shifting one. This time we're shifting this thing 5 to the right and 6 up. That turning point that was at -3 is going to go to +2. It was at -2, it's going to go to +4. This thing's going to turn somewhere there. And it's going to look something, it's going to basically be the same sort of shape, and it's going to look something like that. The inverse of this, all right, the inverse of a straight line will be a straight line. The easiest way to draw this, apart from kind of drawing in this kind of line about which it will reflect, is just to swap the points around. This has got a y-intercept of 4. Remember the name, the point 4 is actually 0, 4. Swap that around, you get 4, 0. All right, this has got an x-intercept of -2. Swap that around, you get 0 and -2. And when you join those up, what we, so I've drawn this blue line, this blue dotted line really badly in a bit of a rush, okay? Because in fact, what will happen is that my inverse line in the exam, all right, my inverse line actually must go through there. If you think about it, that line y equals x, if, for example, -4 lies on the one, it will lie on the other one, because when you swap it around, you get the same point. Okay, and then this one, f of -x, this is an exponential graph with a base less than 1, and it's also been dropped down slightly. This f of -x is going to reflect it in the y-axis. Look at them in my phone. How much need to answer. Okay, I'm going to go through the next question quite quickly. It's sketching some graphs, all right? And this first one is a log graph. The base, remember on log, if the base is not written, it's understood to be 10. Because the base is 10, this will be going uphill. Remember, the base bigger than 1, the graph will go uphill. The base less than 1, our log graph will go downhill. Right, both having a vertical asymptote. This one has been shifted 3 to the left. So, in fact, my asymptote is going to be somewhere here. X equals -3. The graph's going to go uphill. So I'm going to draw the graph in black. It's going to look something like this. Right, at this stage, I don't know these 2 points, but I can easily work them out. All right, how do I work out a y-intercept? I let x be 0. All right, now log of 3, and I can just bring up a calculator and see what log of 3 is. I think I can find the calculator. There we go. Log of 3 is actually 0,477. So it's 0,47748, call it. And this point over here is an x-intercept. And the way I find an x-intercept, I make y0. So I've got log base 10 of x plus 3 equals 0. I'm going to put this into exponent form. 10 to the 0 is x plus 3. 10 to the 0 is 1. So x plus 3. Subtract 3 from both sides. X is -2. Okay, and I've shown all points of interest. Right, the next one is this. It's an exponential graph, all right? It's going downhill, but it's been reflected over the x-axis, right? And then lastly, it's been sort of picked up by 4. What I'm going to do is I'm actually going to draw in the asymptote first up. Now, next up, so I'm gonna just draw for you the little sort of succession of things here. If you just drew a half to the x, it would be an exponential graph going downhill. When you multiply that by a -2, it actually reflects it over and kind of almost stretches it like that. And then lastly, when you add 4, it picks the entire thing up by 4. So our function, our basic shape here is actually going to be something like this. That asymptote, right? It keeps going left and right. The domain is x an element of R. How do I find that point? That's a y-intercept. How do I find a y-intercept? I let x be 0. If x is 0, this just becomes -2 plus 4. This, in fact, becomes 2. All right? How do I find this point? This is an x-intercept. The way I find an x-intercept is I let y be 0. Notice I'm being a bit quick here about not sort of writing all this stuff down. The memo is much more kind of complete, but I'm hoping you're getting the idea. I'm going to solve this equation. It's all about solving equations. That's where we started. Session 1 was on solving equations. I'm going to subtract 4 from both sides. I'm going to divide both sides by -2. I get a half to the x is actually equal to 2. All right. And this is an exponential function. I could take it and use log, but let's try and do it without a calculator. This is actually 2 to the -1 to the x. And this is 2 to the 1. And so I get minus x, 2 to the minus x equals 2 to the 1. Base is the same. It's a 1-to-1 function. So minus x is 1. So x is -1. Okay. All right. Now, the next one is a parabola. And I know it's concave down. I know it's got a y-intercept of 8, found by letting x be 0, right? And I'm going to find the x-intercepts. And the x-intercepts are going to be found by letting y be 0. So 0 negative x squared plus 2x plus 8 is 0. I'm hoping you're going to forgive me for going quite quickly here. I'm just saying x squared minus 2x minus 8 equals 0. And in fact, the solutions are x is 4 or -2. And so the graph's looking something like this. This is -2. This is 4. All right. And the last point that I need to find is the turning point. A number of ways I could do this. I could write this into the sort of turning point form, which we practiced earlier. I could say, well, actually, it's going to be, because of the symmetry, it's going to be halfway between there and there. In other words, it's going to have an x value of 1. I could use the formula x equals minus b over 2a, and I would get x equals 1. Or, and the way I'm going to choose, I know that at this point, the gradient is 0. So in fact, I'm going to work out the derivative. Okay, the derivative of -x squared plus 2x plus 8 y dashed is actually equal to -2x plus 2. I'm going to make that equal to 0. I get x equals 1, as I promised you I would. I now take that x value and I put it into the original, because this is giving me the y value, and I get -1 plus 2 is 1 plus 8 is 9. And I've got this turning point of 1, 9. Okay, the next and last one that we're going to draw is this one over here, and it's pretty straightforward. It's an hyperbola, but it would have been, before it shifted, it would have been strictly in these two quadrants, negative k value, right? Quadrants 2 and 4, but it's now shifted 2 to the left. So this asymptote that used to be x equals 0 is going to be x equals -2. The other asymptote, which used to be the y-axis, the x-axis, y equals 0, is going to drop down by 4, so it's going to be y equals -4. We said that the function's actually going to be in kind of quadrants sort of 2 and 4, so it's actually going to be kind of somewhere here. It's going to have an x-intercept, and it's going to have a y-intercept. All right, the y-intercept's they're both very easy to find, actually. How do you find a y-intercept of any graph? Let x be 0. All right, and if we let x be 0, we get our y-intercept. And again, I'm going to do it quickly here. It's going to be -8. If we let y be 0, we get our x-intercept, and we get -4. Okay, right. Onwards and upwards. Question number 8. An important question, a really, really important question. So we've got these two graphs. We've got f, which is a parabola. We've got g, which is a straight line. And the first thing it says, at the moment, for what values of t will f of x equals t have no real roots? Now, I'm going to do this question in two kind of ways of thinking about it. This is, if we picture the line y equals t, it's a horizontal line. Now, if the horizontal line's down here, all right, then this function will, then there'll be no intersections between f of x, the parabola, and this line. So as long as the line is below the turning point, there'll be no roots. There'll be no points of intersection. In other words, t is less than -25/4. All right. I'm just checking something in my memo here. Yeah. No, that is actually correct. All right. I actually, another way of doing this is to actually say, well, f of x minus t equals 0. Right. Now, at the moment, f of x has two x-intercepts. Having a number over here will shift the graph up or down depending on the sign of the thing. Okay. And now for it to have no x-intercepts, I would need to pick it up by more than 25/4. Right? But now in order for this to be picked up, I actually need a negative number in here. And in fact, again, I need a number like less than -25/4, because that will then add 25/4, which will pick the graph up. So there's kind of two ways of thinking about it, and happily they produce the same result. Okay. For what values of k will f of x plus k equal g of x plus k have roots of the same sign? Now, basically, there's our function and there's our function. At the moment, these two functions intersect one another, once with a negative root and once with a positive root. Okay, by the roots, we talk about the x values at which they intersect. Now, when we add k in here to both functions, the entire picture, both of them are either going to move left or right. Okay, now, if I wanted both these points of intersection to be positive, I would need to move right, one. Move more than one to the right. What would happen is the entire picture, both graphs would move more than one to the right. Okay, the h comes before the t. All right, more than one to the right. Okay, now to move something to the right, we actually need k to be negative. So k less than -1. That will move it more than one to the right. Alternatively, to get both points of intersection negative, I need to move more than 4 to the left. All right. So, or more than 4. To move it more than 4 left, k must be bigger than 4. This is challenging. I don't think it's impossible, but it's slightly tricky. It definitely relies on sound understanding of the shifting of functions. Then for what values of of x is f of x bigger than 0? We just remember f of x actually means the y value of f. All right, but we're going to express our answer in terms of x. Where does the parabola go above the axis? It's basically what we're saying, y value positive above the axis. So, and the answers are clearly here, that way, or that way. X less than -2 or x bigger than 3. Okay, right, the next one, and I think I've created a new page for myself so we can see what's going on here. For what values of x is f of x bigger than g of x? And again, just to reinforce that, by f of x, we're actually talking about the y value of f. Where's the y value of f bigger than the y value of g? If the y value is bigger, it means it will be above, all right? In other words, where is f above g? Well, f is above g everywhere to the left of minus 4. All right. So everywhere to the left of minus 1. All right. Or everywhere to the right of 4. So x less than minus 1 or x bigger than 4. Okay. For which values of x is the product of these two things negative or 0? And remember, to get a negative product, we need one to be positive and one to be negative. Remembering that this is the y value of f times the y value of g. We actually need them to be on opposite sides of the axis. So where are they on opposite sides of the axes? Well, less than minus 2, the parabola is above and the straight line's below. After that, they're both below until this point over here, which is 1. From 1 to 3. From 1 to 3, they're on opposite sides, right? The parabola is below and the straight line is above. After 3, they're both above and they both remain above. Okay. Then this next question is this vertical line AB, right? And it's got this kind of length there. Okay. And I'm going to find a sketch at the end just to sort of show us that we've got the right answer. But the thing is that this point over here must have the coordinates x, whatever x is, x squared minus x minus 6. So over here must have the coordinates x, 2x minus 2, because it lies on the line with that rule. That's really, really important. So the length of AB is actually just going to be the bigger y value minus the smaller y value. AB is actually going to be 2x minus 2. Take away x squared minus x minus 6. Okay, and that all comes out in the wash to negative x squared plus 3x plus 4. Okay, now I want to find the maximum value of this. This itself is a parabola, a kind of concave down parabola. The easiest way of finding the maximum value is to actually differentiate it. So I'm going to work out the derivative of AB with respect to x. And I get negative 2x plus 3. I'm going to make that 0. And I'm going to solve for x. And I get x equals 3 over 2. So the longest line, the longest length that AB can have is actually at 1.5. And that maximum length, just put 3 over 2 into the formula for the length of AB, and I actually get 6.25. Okay, I'm going to just show you a sketch here, which I hope is going to reproduce nicely. That what I can do here is I'm just moving the line across, right? And what you'll see, okay, is that when it's getting longer and longer, that green dotted line. When I get to 1.5, it gets to 6.25, and after that it starts to get smaller. Okay, so that's kind of where it moves. It gets longer and then shorter, and it's at its maximum there. You might be wondering what that little dot at C is. That is actually plotting the length as I move across. So it's actually plotting the length of this line. Notice the length of the line is 0 there. It's longer and longer and longer and longer and longer to 1.5, and then it starts to get shorter and shorter and shorter. And we've found the maximum length of that line AB, where they are the maximum vertical distance apart. Okay, we are very, very nearly there. And so we've done that one. This one is finding equations of functions. Very, very straightforward. You've obviously got to know what is this thing? Well, it's a straight line. Standard form y equals mx plus c. Right? The gradient, it's dropping 8. It's running across 4. The gradient is negative 2. And I wanted to go through one of these points. As you know, I like to use this form. Y minus a y value is the gradient x minus the x value, x minus minus 1, x plus 1, right? And that all comes out in the wash to y equals negative 2x plus 3. And if I just look at that, it kind of makes sense. I expected a negative gradient. I also expected a positive y-intercept. This here is a parabola. The vanilla form or the parent function is ax squared. But this one has been moved because ax squared is actually here with a negative a value, okay? We just bear in mind we're expecting a negative a value. We don't have to put a negative there. The a value will come out right in the wash, okay? So how's it been moved? Well, the turning point of the vanilla one's there. It's been moved 4 to the right and 1 up. How do I affect that change? To move a function to the right, I subtract 4 from all the x values. To move it 1 up, I add 1 at the back. Now, every single parabola that turns at 4, 1 can be written in this form. I'm now going to find out the specific one with the specific value of a by substituting in this point. Substitute in 2, negative 7. And when I do that, all right, I get negative 7 a 2 minus 4 all squared plus 1. And I get negative 8 is actually 4a. So a is negative 2. So in fact, my answer is actually going to be negative 2 x minus 4 all squared minus, x minus 4 all squared plus 1. They're going to likely want it multiplied out in standard form. Remember how many times I've said it's useful to be able to square a binomial quickly. X squared, but it's going to be negative 2x squared. Negative 8x, that's going to be multiplied by minus 2, so that's going to be plus 16x. And then 16, negative 32, plus 1, negative 31. Okay. Onwards and upwards to our next two and our last two, to where we're finding equations. I think maybe they're not the last two, but this is a cubic, right? But it's a cubic that's got x-intercepts of 3. So it must factorize to something ax minus 3. And then it's got a repeated, and I'm including this one on with intent because often people aren't really sure how that works. We actually need to have that squared. And then exactly the same idea as last time, we're going to substitute in the point. So when a cubic turns, or even a parabola turns and has a repeated root, you need that bracket squared. Substitute 236. When we do that, again, just to maybe save a little bit of time, we actually end up with a equals minus 1. And we end up with a final answer, because this is just algebra now. Multiplying it out, we get minus x cubed minus 5x squared plus 8x plus 48. Okay, I'm going to ask you just to dig deep and hang in there for the last probably 4 more minutes, right? This is a log function. How do I know it's a log function? It's got a vertical asymptote. I can tell you that this base is going to come out bigger than 1, right? This log function is moved 4 to the left. How do I move it 4 to the left? Plus 4. Now, as I've done every single time, I'm going to substitute in a point. Substitute for 3. And when I substitute for 3, I get 3 equals log base A of 8. Right, I want A. I'm going to take it out of log form into exponent form. The base is always the base. A cubed equals 8. All right, and I get A equals so I get A equals 2. And I get my final answer of y equals log base 2 x plus 4. There, hyperbola, standard form k over x. However, it's shifted. It's shifted due to the left because the asymptote said x equals minus 2. I'm going to go plus 2 because that will shift k over x 2 to the left. It shifted down 1 because the horizontal asymptote said y equals minus 1. What do you think I do now? Yeah, I can hear you saying it. Substitute in the point. So we now substitute 4, -2. And I'm going to ask you, I'm going to tell you, I'm going to write down the final answer, but I'm going to ask you, do you expect a positive or a negative k value here? Absolutely. In those quadrants, it must be a negative k value. Final answer, -6 over x plus 2 minus 1. Okay. And then the very last one, and this is an exponential function, and I've put a little bit of a curveball in here. Remember the vanilla parent function, ab to the x, right? This one is moved, and the way I know it's moved 4 up because the asymptote's at 4. Now, often and typically they give us a y-intercept. I haven't done that yet, but I just want to show you that you can do this anyway if you know how to solve equations. I'm going to sub in this point, 1, 3. 3 equals ab plus 4. And now I'm going to sub in this point, -2, -4, and I get -4 equals ab to the -2 plus 4. I'm now going to simplify both of these equations. So the black one, I'm going to subtract 4 from both sides, and I get -1 equals ab. The green one, I'm going to subtract 4 from both sides, and I get -8 equals ab to the -2. All right, and now I can solve these two equations simultaneously. What mathematical operation will eliminate the a's? And indeed, if I divide these equations by one another, I get 1/8, and here I get no a's, which is a cause for celebration. B to the 1 divided by b to the -2. Remember, I'm going to subtract my exponents. I get b to the 3. So I get an 8th as b cubed. I cube root both sides, I get b equals 1/2. Here I've got an equation with a and b in, so a times b is -1. So in fact, a must be -2. And my final answer for this one, y equals -2 times 1/2 to the x plus 4. Okay, and the very last question, which really just tests something here. We've got a function where the domain of the inverse is that, and the range of the inverse is that. And the question says, what's the domain and the range of the function? Well, remember, domain is always around the x values, right? But the domain of the function will be the range of the inverse. -3, 8. Exactly the same, round bracket, square bracket. The range of the function will be the domain of the inverse, but expressed with a y. Okay, and folks, that brings us to the end of, in fact, all the live streams for paper one. I am aware that a whole lot of matrics in South Africa, that those that are writing IB will be writing paper one on Monday, right? The ones that are in DBE schools will be writing paper one on Friday. I want to wish all of you good luck, right? Mag die Here julle almal seën. May God bless you all. Nkulunkulu anibusise nonke. And obviously good luck to the Springboks. And then please, these live streams I found them difficult because I'm talking to a screen, in fact, to a couple of screens. And I really would love some feedback. So if you've got a minute and you want to just drop me an email, I do want to thank a young lady who did send me an email just thanking me, and yeah, that was really uplifting. I'm not necessarily looking for thank yous and praises, but I would love to get your feedback. Was it too quick? Was it too slow? I suspect it wasn't too slow. I do think that if you'd done the questions beforehand yourself, then you'd be better equipped. All right, I'm praying for each and every one of you on Monday and on Friday. For kind of clear heads and that you're really going to do well. But my late mother used to say, God helps those who help themselves. So also do some work. Don't just rely on the power of prayer. Do some work and on the power of prayer. But I'll be praying for each and every one of you for great success in your exams. We do have live streams carrying on next week for 3 days. We've still got 3 paper 2 topics to continue to complete. I suspect many of you will be focusing on paper one for now, but you can watch the recordings thereof later. All right, take care, everyone. Have a great day, and all the best. Bye.